Okay, so for today, we'll do 2 pages. And that'll leave us with 2 pages for Thursday. Um, so yeah, today we're focused on the process of use substitution. So yeah, that's what this homework is going to cover. So hopefully you will have gone through the lectures and seen how use substitution works. I don't need to completely, well, I mean, really like the easiest way to kind of explain it is just show you how to do it, I would say. But yeah, so the idea is that you would take, well, the idea is that you're trying to simplify the integral that you are are faced with um, by converting things over from uh, the X world over to the U world by doing a sort of a replacement. So you choose something to be your U, and usually this choice is going to be a part of the function that you're given. In harder examples, this may not be the case, but usually we give you these easy problems where the U is going to be a part of the function. So then you take that and then you calculate what the du is, and then you convert over both the function and the dx over to a function for u and a du. And then hopefully the resulting integral that you get is easier to integrate. And so then you can perform the integration. And then afterwards, you will need to do a back substitution. Okay. So like looking at this problem, there's really only one reasonable choice for what u would be, right? It would be the denominator. It would be the x squared plus 3. And you can then check like what happens when you take the derivative. You get 2x dx. Okay, and so what's useful about that is it's going to absorb this x here. The only thing is that we have to actually introduce a 2 in order to convert everything over completely. So one way we can do this is by multiplying and dividing by 2. And so we do that. And then we can now rewrite the integral. So 2x dx gets converted into the du. And then you have a 1 over x squared plus 3. That's a 1 over u. So this is the integral that you get when you perform a u substitution, this u substitution. And then the next thing is going to be just integrating it. So this is going to be ln of absolute value of u. And then you want to back substitute it because the original problem is phrased in terms of x. So the answer should be phrased in terms of x. So you want to back substitute. And so you would get a x squared plus 3. And then you would have a plus c at the end. And there's technically one additional thing that you can do to this problem. So notice that these absolute values are unnecessary here because the expression inside the x squared plus 3 is always positive. So you can actually replace out those absolute values. Oops. It's not something that you need to state, but if you see that, that can be helpful if you're gonna like work with the answer afterwards. Like, yeah, it can be easier to deal with not having an absolute value there. But okay, so this is the answer for A. All right, questions? Hopefully the process is comfortable. Yeah, we're gonna get comfortable with
Um, could you explain how you got the 2x one more time on the du is equal to 2x dx?
that. Oh, so what I'm doing is I'm taking the substitution that I'm trying out, and I'm taking the derivative of it. So this is like the derivative from like the differential section. Derivative of u is the u. Derivative of this is 2x, but then you have a dx.
Okay, yeah, that makes sense. Thanks.
Yeah. I guess, yeah, one thing I'll say is like if you're not comfortable with U sub yet, then you might find yourself trying different things for U and seeing whether or not they work out. And if they, so there might be a bit of like trial and error in this process until you get comfortable enough with like, until you get enough experience with the U substitution. It may be that like you have to try out different U's and see if they will work or if they don't. And you just, yeah, there's a bit of trial and error in this until you get uh, enough experience to like be able to tell right away like what should be the thing, like, or what is the most likely thing that would work. This can especially happen if you actually get a more complicated problem than what shows up in the homework. Okay. Well, so for B, so I want to encourage you to think about what the U should be for this problem. Give you guys a few seconds to think about it. And if anyone wants to like say it or type it, like that would be good. I would encourage you to chime in.
Would it be 7? Wait. Would it just be 7 sine, right? Or would it be 7 sine tangent?
Okay, those will be very complicated. So one thing to think about is whatever you choose as your U, you're going to end up differentiating it. So one way to think about it is you want the derivative to show up in the function. That way, it kind of gets absorbed when you replace the variable with the U. Okay, and Jose also suggested something, but that suggestion also will not work. So, okay, I'll tell you what it is. Your U should be tangent of W. Okay, so it's just the part inside the sign. So if you do that, then what happens is the derivative is going to be the secant squared W. And so this will drastically simplify the integral. Okay. So hopefully you agree that that's what the du is. And so when you perform the u sub, I think I can pull the 7 out. So you'll have sine of u du. That'll be the result of performing the u substitution. Okay. And so integrating this, you get -7 cosine of u. And then we can back substitute -7 cosine of tangent of w. And then tack on the plus c at the end. Okay, does it make sense now that I've told you what the u is, the whole process? Okay, good, great. All right, yeah, so now for C, it's similar. U is gonna be something, du is gonna be something. So maybe I should actually let you guys, I should pause longer for you to actually, so since it wasn't quite so clear what u was, what do you think u is gonna be here? All right, keep in mind that you're going to take a derivative and you kind of want the derivative thing to be something that also shows up in the problem.
Would this one be e to the 7x to the 4th plus 2x?
Mm-hmm. You captured too much by doing that, because if you do that, then the du will be e, you'll also have the exponential function there. So that is too much. Instead, you should try just the exponent. Okay. And then, so this is kind of where like the this polynomial in front is kind of special with respect to the exponent. So it just matches up very nicely, sort of coincidentally almost. So when you take the derivative, we get 28x cubed plus 2 dx. Kind of put a dx around both of the things and see that like this is twice of this. So if we actually then introduce a factor of 2 into the integral, then the du is going to absorb this in front, and then we'll just have e to the u inside the integral. Yeah. Okay, so then we go ahead and integrate that, which is pretty easy. And then we substitute it in. And tack on a plus c at the end. Yeah. So I think it's a good thing that I was actually asking you guys what you think the u should be. I forgot to really ask the other class. There's a chance that they don't know how to do u sub. But yeah, so you see that like it is a bit of trial and error. So what you can do is you can guess something and just try the process out and see that like that there's going to be a mismatch. So when you suggested the e to the some power, you would then compute the du and you'd see that like you ended up capturing too much because you can't fully replace out the du. So hopefully like just practice a few things. You can find stuff from like the Paul's online notes, that guy's website, for example. If you need extra practice for u sub, I can, recommend that. Okay, so now D and E, they're actually a bit more complicated. So these first three are actually what I would consider a bit simpler because it's kind of like it's just directly you calculate your u, calculate your du, and then you can just substitute things right away. With a D and E, you actually need to do something additional. Because it turns out that like this t and this x to the fifth will kind of linger around when you do the substitution. So for D, for example, well, there's only like two real suggestions that you could try, right? You could try u is equal to the square root of 5 plus t, and you could try u is equal to 5 plus t. But if you don't know this trick, then you might not be able to figure out how to convert everything over completely. And I'll tell you what the substitution should be. It should be the 5 plus t. Okay. And so du is just going to be dt. Right. So the thing that makes this not clear is this substitution is going to replace the stuff inside the square root, but it's going to have this t stuck around. And so really what you need to do is you need to figure out how do you convert t so that it can be written in terms of u. And the key fact is you're using this rule that you just set up. Well, what you can do is you can manipulate the rule and just subtract things over. You'll get t is equal to u minus 5. And so that is how we perform the u sub in this case. So the t gets converted into u minus 5. The square root gets converted into the square root of u, and dt is equal to du. So we can convert the dt directly into du. And now this guy we can integrate because we can write this as sort of a polynomial in terms of u. All right, so this is just u to the 3/2 power minus 5u to the 1/2 power du. And so we can then use the reverse power rule to integrate this. So this is u to the 5/2 times 2/5 minus 5u to the 3/2 times 2/3. And then we could back substitute. 2/5 5 plus t to the 5/2 minus 10/3 5 plus t to the 3/2 plus c. Okay. And so, like, notice what happened in this problem was we converted this thing inside the square root so that it was just a single variable so that we could then regroup things. Like, normally you would think that this transformation does barely anything. But here it was actually extremely necessary because we could convert this t to be a polynomial in terms of u, in terms of the variable, and then this would just be that variable, and then we can rewrite it as the integral of a polynomial, which is very easy to integrate. Whereas the way that it is written like this, it's stuck. You can't really do anything with it. So this is kind of an interesting example of an integral. Okay. So hopefully that made sense and you're comfortable with it, because E is going to add on to that now. Okay, E is very similar. So you see you have a square root, you have x to the 5th. Okay, so like before, we would try a few things out, and really like the first guess that you should make is either like just the stuff inside the square root or the whole square root. And you could think like the square root itself, that's going to be way too complicated. So you would try use the stuff inside the square root. And then you would take the derivative, 2x dx. Okay, well, that's going to capture some of this x to the 5th, but not all of it. And so that's where we kind of have a bit more complexity here. So let's see what happens. Okay, so first of all, what would happen is I need it to have 2x, so I'm going to introduce 2 by multiplying and dividing. And then when we try to convert it over initially, 2x dx will get absorbed and become a du. So the parts that are not absorbed are going to be x to the 4th. And then this square root is going to be a square root of u, du. Now, the thing I'll say about this is that this is very improper, the way that this is written. You'll never see this in a textbook where it like has two different variables. This is like a hybrid between being an integral in the x world and being an integral in the u world. And so it's very wrong to write this, but I think it's illustrative of what we're trying to do. What we have to do now is we need to convert somehow this x to the 4th so that it's written in terms of u. And the only thing that we know is this rule. Well, thankfully, hopefully you see, there is a way to do that. Okay, so if I solve the x squared, I'm going to get u minus 1. And then what I can do is I can square both sides. So then I get x to the 4th is equal to, and then in this case, I want to expand this out. So u squared minus 2u plus 1. Okay. And so then converting this over completely, well, to save space, what I'm going to do is I'm going to distribute this x to the 1/2 power into the polynomial. So we'll have u to the 5/2 minus 2, u to the 3/2 plus u to the 1/2 du. Okay. So yeah, textbooks usually will not write this step, but they would write it with the x to the 4th converted over, or they would write this. They would just go from one to the other without that intermediate thing that I wrote. Okay. And so lastly, you have to integrate this. Well, come on, integrate and then back substitute. So integrating u to the 7 halves, 2 over 7, minus 2u to the 5 halves, 2 over 5, plus u to the 3 halves times 2/3. And we can see there's a cancellation. We can cancel the division by 2 with 2 is the numerator. And then we can back substitute. So 1/7 u is 1 plus x squared. And then we just continue with the back substitution. Plus x squared to the 3 halves, and then plus c at the end. Okay. Right. Okay. Any questions? No? Right. So now then we're gonna switch over to definite integrals. Okay. So what we've just been doing are indefinite integrals where there aren't any limits of integration. Now we have definite integrals, and we're going to try doing u substitution in order to calculate these integrals. So with definite integrals, there's actually two different approaches that you can take as a result of the fact that we're doing u sub. Like there's two different processes that can be done. So I don't know how to really express this, but so you're starting with a definite integral. Let's say, like, let me just write this abstractly. So say you're given a definite integral. So you're given these limits a to b. What you can do by performing a u substitution is you can convert this over to some other function. So in terms of u du, but in this case, it would be an indefinite integral. You don't have the limits. So that's, and then what you would do is you calculate what the antiderivative is, and then you would back substitute. And by back substituting, you would then convert yourself over, you'd convert yourself back to the x world. So you then have the antiderivative of the function f, which you could then evaluate. You could then perform the evaluation in the x world, and that would give you your answer. So this is the first approach, right, where the evaluation happens in the x world. The second approach is when you perform the u sub, not only do you convert the function over, or the integral over, but you also convert the limits over. And one thing is that these limit values, they don't need to match up. So they might convert into some other numbers, n and m. Okay, but because you can convert those limits over, you would then be able to calculate the antiderivative, but then you'd be able to evaluate in the u world. Okay, so these are the two different approaches that you can take. One way we get to evaluate in the x world, the other way we can evaluate in the u world. And really, they're equivalent to one another. So you should expect to get the same result. Yeah. And I don't know which approach is more, say, convenient, but I've gotten kind of used to using the second approach where we convert the limits over. But sometimes it might make sense to actually find the antiderivative back in the x world before you evaluate. That can happen sometimes, but for at least for all the problems on the homework, the second approach is the way that I'll go. Okay. All right. So now let's go ahead and perform the use up here. I should also say, like, you don't necessarily know like that use sub will work. One thing that you'll encounter if you go on to Calc 2 is you have this problem where you learn a whole bunch of different techniques. So Calc 2, one of the first things you learn in Calc 2 are a variety of integration techniques. Use substitution is just one of them. And so as before that, like what did we do before that? We were just pattern matching based off of our knowledge of derivative rules, right? We were just reversing derivative rules. So we have that, we have U sub, and then you start learning other techniques in Calc 2. Then you end up having this issue of how do you know which technique to apply? Well, the answer is you don't. You have to just try out different techniques and see which thing works. And maybe with some experience, with lots of practice in integrating different things, you might gain some intuition for like what method you think will work. But ultimately, it comes down to just trying out the technique and seeing if it works or if it just makes a huge mess, in which case you kind of back off from that and you think maybe try a different approach instead. So like with USub, like I'm in this case, like for this problem, for this homework set, we know like all these problems should involve USub, but out in the wild, if you're just arbitrarily given an integral, you don't know that that's the case. So you kind of will expect to try out different things to see whether or not it'll work. But here we can kind of reasonably assume. Okay. So, okay, U sub. What should our U be in this case for this cosine of pi? Well, the thing is that we're used to thinking of the cosine, sine and cosine functions as just having a variable inside. So we really kind of want to absorb this pi. And so that's what our substitution is going to be. We just let it be the stuff inside the cosine. So then du is going to be pi dv. Okay, so that tells me I need a pi inside my function in order to perform the u sub. Okay, so I multiply and divide by pi. Okay, and then what is that going to turn this integral into? It'll be cosine of u du, which we can then integrate. But let's also convert the limits. Okay, so the way that we convert the limits over is, well, these are places in the x world. And then we use this rule to figure out what is the corresponding place in the u world. So 1/2. So this is like saying v is equal to 1/2. If that's the case, what is u going to be equal to according to this substitution? Well, if v is 1/2, u will be pi over 2. And if v is 2, then u is going to be 2 pi. So there we go. We've converted the integral over completely. And we can then go ahead and integrate this. So the cosine, when we integrate it, it becomes sine of u. And then we can evaluate this in the u world by using these new limits. And one thing I'll do is I will pull the 1 over pi out. So I'm only evaluating the sine of u. So I plug in 2 pi into that, and I get 0. Minus, if I plug pi over 2 into sine, I'm going to get 1. So I get minus 1. And so finally, I get the answer of negative 1 over pi. Okay. All right, so now the next ones are going to be a little bit faster because I won't have to explain as much. U, in this case, and du. Okay, well, I want to at least pause and let you think about what you should be in this case. So if you think you know, then Feel free to say something or message it.
Would you be everything on the bottom?
Be careful when you say everything. Do you mean everything, including the
Uh,
square?
um, no, not the square.
Not the square, that's right.
Let's
Yeah.
go. Okay.
Yeah. And Jose, so you said you said this thing on top. Well, the problem is that that really is going to not work because if you then take the derivative of that, if you take the derivative of that, that's going to cause issues for like trying to capture the denominator. Like there's a mismatch there. Instead, yeah, you need it to be the thing inside of the square, not including the square. If you include the square, it becomes a huge mess, right? So instead, you have this, then you take the derivative and you get something that is related to the numerator. So in that way, we can end up absorbing the numerator. Okay, so we get 18x squared plus 3. And that is simply a multiple of the top. So what we can do is we can introduce, right? We just have to multiply top by 3, which, well, requires that we then multiply and divide by 3. And so now we can convert this over. So we get a 1/3 in front. And then the function inside, well, the numerator and the dx get converted into du. And then, well, your numerator is going to become just 1 in that case. And then the denominator, well, you absorb the part of the bottom. So you end up with this, okay, 1 over u squared. And we can go ahead and integrate this. I'll fill in the limits in a second. So integrating this, we'll get u to the negative first power, and then with a negative in front, which you would then evaluate. Okay. So, and I'll pull the negative 1/3 out just for convenience. All right. So now we think about what the limits are going to be. So x is 0 means that u is going to be 3. And if x is 1, well, that's going to mean 6 plus 3 plus 3, 6 plus 6 is 12. So that means u is 12, the upper limit. Okay, so we evaluate from 3 to 12, and we can just go ahead and compute this. So this is a little bit of a pain, but it's not as bad as I think. There's like a calculation I gave up on, like that's for like tomorrow or Thursdays. Okay. Yeah. All right. So then if you put it over a common denominator, you're going to get 12, 1 minus 4. So you get minus 3 over 12. And so then you end up with 1 over 12. Yeah. Very good. Okay, so that's how you do that. For C, you want to, well, U is going to be something, du is going to be something. So what do you think would make sense? Right, keep in mind that the du is going to, like, you kind of want like whatever you pick to be your u, you also need to keep track of what the derivative is going to become. And you would hope that that also is something that gets absorbed, or that shows up in the function to be absorbed. So I don't know if this one is tricky or not.
Is it 2 sine?
You can go a little bit simpler than that.
Just sine then?
Just sine. Yeah, just sine. Good. Right, so letting it be sine, then du is going to be cosine t dt. And so this whole piece ends up getting replaced and becoming the du. And I can pretty much pull the 2 out. And sine cubed, that becomes u cubed. And the stuff at the end becomes du. And then we can figure out what the limits are. So sine of 0 is 0. Sine of pi over 2 is 1. And we can just integrate this. So this will be 2u to the 4 over 4. So what I'll do is I'll simplify this, u to the 4 over 4, but then times 2 is just going to be u to the 4 over 2. Evaluate from 0 to 1. And so that's going to be just 1/2. Yeah. So it wasn't wrong to say 2 sine. It's just that well, it would have been pretty bad actually, because you would have to cube your u. And that'll introduce a whole bunch of powers of 2. It'll get a little bit messy, but it would at least be doable. So sometimes there can be multiple choices for you, but this one is the easiest way to go about it. Okay. All right, and lastly, D. So I want to draw the parallel for you. When you see, or at least when I see this, my mind is immediately led to this fact, right? I'm immediately led to this integral and the knowledge that this is arctangent. Okay. And that's primarily because, well, that's because of the shape of this function. You have 1 plus stuff squared, some variable squared. So 1 plus stuff squared, and then the numerator doesn't involve any variables. It's just a constant that we can just pull out. So then that's why it makes me think of this right away, which makes me think of arctangent right away. And so really, like, our aim is kind of to make this look as close to this function as possible. And that will tip you off on what the u sub should be in this case. You want the 2x to convert to become just what? A variable. So you want that to be the u. 2x you want to be u. And then du is going to be 2 dx. And so this is going to take one of the 2's here. And so when you convert this over, you'll get 4 over 1 plus u squared du, which is fine. We can then just take the integral. So this is 4 arctangent of u, which we would then evaluate. Okay. And so now let's think about how, what happens when we convert these limits. Well, we just multiply by 2. That's pretty easy. So 0 to 1. Okay. 0 to 1. That's easy. Now evaluating. That's what we need to think about arctangent. So arctangent of 1, that means what angle, when I give it to a tangent, will give me back the value 1. And so you should think pi over 4, the 45-degree angle. Tangent of pi over 4 is 1. And evaluating arctan of 0, you think again, like, yeah, what angle will give me 0 when I evaluate tangent on the angle? Well, 0. So tangent of 0 is equal to 0. And so there we go. And so your answer is going to be pi. Okay. Yeah, so that's all I want to do today. Are there questions on anything? Okay. If not, I'm going to stop recording.